And let's say that the pulley has a mass of 3m and a radius of capital R. This is a heavy pulley. Because it's a heavy pulley, it has inertia. You should already know how to calculate the moment of inertia of a disk. It should be in your notes. But in case you don't remember, because memory eludes you, a disk is 1/2 mr squared. Be careful. I am intentionally trying to manipulate you a little bit. Moment of inertia of the pulley is about its total mass and its radius, which is why I put little m and little r there for the moment of inertia, to differentiate it from the fact that my pulley has a mass of 3 times some value I call m. You understand? Because I'm going to probably hang a block here that has a mass that is also some multiple of m. So that in the construction of our problem, we have some kind of relationship between the mass that's being hung and the mass of the pulley. You understand why I'm doing it that way? This is why people construct problems like this. First, it's make sure you understand. I could put 20 grams and 100 grams. I could do that too. I just don't want to. In fact, I'm thinking about doing the whole problem in terms of I, just to make it more confusing for all of you. Because this is the level of work you're supposed to be able to do. Now, in this arrangement, we understand what's going to happen, right? It's not a surprise. The box is going to go downwards and this thing's going to spin. We understand that is what I just showed you. I just turned it on its side. We all good? So it's the exact same thing. It's just hard for me to draw something flat spinning and something hanging off the edge. So I'm drawing something that's easier to see. Let's handle the stuff that we know about first. We know about the block that's falling because that's a Newton's law problem. What I mean by that is you know that, let's put that over there. You know that net force equals MA. The explanation for why the box moves is forces. Energy can explain its velocity and where the energy went. It's a good conversation. But why it moves, because gravity acts downwards. How effective gravity works has to do with the fact that there's more than one force acting on the box. There's a downward force of weight and an upward force of tension. Together, these two forces determine the acceleration of the box. If I make downwards positive, then I'm looking at 2 mg minus tension equals 2 ma. Something that you probably already did in your notes because you're way ahead of me because you guys are super smart and recognize that I'm expecting you to know first semester physics. Now, that's insufficient to solve this problem because we don't know what the tension is. And as we already deduced, the amount of tension here will depend on the inertia of the pulley. Right? That's what determines the whole thing. It will accelerate slowly if the pulley has lots of inertia, and it'll accelerate super fast if the pulley has very little inertia. I should see that in my answer. So let's handle the pulley. Newton's law for the pulley is different than you might expect. The net force on the pulley is 0 because the pulley doesn't go anywhere. Right? We saw it. It just sat on the table. This pulley will also not go anywhere. Now, don't assume that because the net force is 0 that there are no forces acting on the pulley. It should be clear that the pulley is experiencing a downwards force of tension right there. I drew it exaggerated, but it should be the same size as this tension. I exaggerated it so that you would see it. That is not the only force acting on the pulley. The pulley also has weight. And something is pulling up on the pulley. I don't know what you want to call that. Normal force? Force from the mount? I don't care. Something is acting on the pulley. But the net force on the pulley is 0 because it stays there. It doesn't go anywhere. And that part, it's, the pulley's translationally at rest because it doesn't change location. But we all know that the pulley is going to rotate, and that's because the net torque is unbalanced, which means it's going to accelerate. Newton's second law for torque. I introduced it about a week ago. I'm going to really go into it today. We've done this side of Newton's second law, or Newton's law for torque before. We did static problems. And all the problems we did, we set that equal to 0, but this case is not going to be 0. This object accelerates. And because it accelerates, we're going to have to evaluate the torques and now deal with them being unbalanced. In this problem, there's only one torque. Right? When you look at the 3 forces acting on the object, they all don't do torque. This one acts at the center of mass. There is no torque arm. So it does not apply a torque to the pulley. I'm expecting you to be able to explain this. So for you guys who are, if you know that that's obvious, great. If you didn't know that that was obvious and didn't have an explanation, I'm giving you the explanation. You understand how all of these explanations tend to be things that show up on tests. This force, whatever you want to call it, also does not apply a torque. It acts at the center of mass. And that's also the pivot point. So there's no torque arm. The tension does cause a torque. It does not act at the pivot point. It acts away from the pivot point. So it's going to cause the system to accelerate. And although I know all of those things seemed obvious, I know what your homework probably looked like, and I know that many of you would have said, I don't know where to begin this problem. I don't know what you're talking about, Mr. Shelton. Well, the look on your face says that this is all straightforward. A torque has 3 parts. The torque arm length, the size of the applied force, and the angle between the torque arm and the applied force. So the torque arm looks to be this distance here to here, and it is R. The applied force is the tension. And it's pretty clear to me that that tension's at a 90-degree angle. Truth be told, all pulleys will have a string that comes off of them at a tangent. No matter how you try to pull on a pulley, the string will always come off at a tangent. Always. No matter what you do. Because if you try to move the string to come off at a shallower angle, it just wraps around the pulley until it's still coming off at a tangent. So if your pulley is a circle, the tensions will always be tangent to that circle, which means that for all pulleys, it's always going to be the sine of 90 degrees. The force here is a tension, and the torque arm length is R. I'm going to make this the positive torque, and I'm going to make sure that this direction I also call positive. So it's in agreement with the motion of the box. Do you remember for net force how you have to make a uniform direction? Now this direction of torque is into the board, so I'm making into the board positive. But I want to make sure that what I call positive for one object is the same as what I call positive for the other. So just because it's into the board doesn't mean that it has to be negative. I can determine what is positive and negative. I'm going to set that equal to I alpha. That's Newton's second law. This is the only unbalanced torque acting on the system. Now, we've done problems like this before, but obviously they have to be more thoughtfully considered because we have to go through and create the torque for each force that acts on our spinning object. That's an extra step. But what also is an extra step? Moment of inertia. And lastly, we have an angular acceleration here, not a linear acceleration. When we did this first semester, if you'll recall, we might get a bunch of different force equations, but they usually all had A in them. Do you remember that? Well, now we don't. So now one of the things you will have to do is ask yourself a very important question that you will often forget, but I want to rub it in your face a little bit. Is this a true statement? We talked about this with rolling. We talked about this with displacement. Now we're talking about it with acceleration, but they are all the same question. Can we say that a rotation of our pulley is equivalent to our box moving a circumference? That's what you have to ask yourself. If this unwinds one time, will the box go down one circumference? Will one circumference of string wrap around the outside of our object? You guys understand what I'm trying to say to you? I'm trying to get you to evaluate, does the motion of the box correspond to the motion of the pulley? Does its rotation directly affect the motion of the box? What do you think? Is that a yes or a no? I think so. I think if we look at how much string it would take to wrap around here, it would have to be a circumference of string, and the box would change that circumference if it unwrapped one time. That's the metric I want you to use. So if that's true, then I have a way to transform this from angular acceleration to linear acceleration. Or if I want, from linear acceleration to angular acceleration. Read your problem and determine, do you want the acceleration of the box or the acceleration of the pulley? Now I'm going to pick one. I'm going to pick the box. But the problem could pick the pulley. Do we understand? So picking the box, that means I'm going to solve this for the angular acceleration in the terms of our problem. Capital R. Capital R represents the radius of this problem. So, we good so far? All I've done is a bunch of algebra. I know it's a bunch of letters. But look, we're going to try and do the same thing we did before. If you'll recall, what we did before was combine these two equations and cancel out t. You remember doing that? I want to do the same thing. So I want to get t by itself. Now, I know you're not going to understand why I'm about to do this, but it's probably because I have experience and you don't, but it also might be because you don't have vision. Have a little vision. Have you noticed that every single moment of inertia has a r squared in it if the object can spin? Have you noticed? Does it make a little more sense to you maybe to combine the moment of inertia with the r squared? If every single moment of inertia has an r squared in it, it is likely that the r squareds might cancel out eventually. Now, I know we're out of time, and I see all of you rubbernecking, but what we're going to do next, I think, is pretty obvious. Do you see what we're going to do next? I hope so. I'm going to add these two things together and get this. And I know you have to leave, so I'm going to leave you with this to contemplate and think about. I combined them and factored out the A. Net force, inertia, acceleration. Do you see where the inertia ended up? Ask yourself, when you make this bigger, does the acceleration get smaller, just like in our demonstration? All right.